In this video, we're going to do a few example antiderivatives here of these reciprocal functions. People like to call these anti-deriving logs. They just don't look like logs just yet. So this first one, I'm going to actually show you two ways of doing it. It might be a little bit confusing, so you might want to buckle up a little bit for this first one. So let's use the first process we did. Okay, the first process we did in that previous example is I put the 3 where it is, I'm not touching the 3. I put the bottom part of that fraction into a log, and then I divide by the derivative of what's in my bracket. And then I put a plus c on the end. Okay, lovely. You could call that done. Now, the issue is ln of 2x could be a lot more difficult to solve than if it was just ln of x. So another thing we can do is, before I anti-differentiate this, so I'm going to say or, let's choose a different technique, I could say this is the same as 3 over 2 times the integral of 1 over x. And all I've done is I've stripped out that 3 over 2 fraction, because that's just a number. Okay, I've just stripped that 3 over 2 out of there, and I've left the 1 over x in there, because really I'm just integrating stuff to do with the x. Okay, that's the most important part. Now, if I do that, what's going to happen is that's going to be 3 over 2 ln x divided by the derivative of my bracket, which is 1. And what I'm going to end up getting is 3 ln x over 2 plus c. Now, you might be looking at this and you might be saying, hold up, this is not the same as this. Well, yes, but, okay, let's show you what's actually happening. Again, put your thinking cap on. What I'm going to do now is I'm going to show you what I can do with this function here. So this is just 3 over 2 bracket ln of 2 plus ln of x. What have I done? Log laws say that I can strip that multiply back out to an add. Then I'm going to multiply these out here. That's 3 ln 2 over 2 plus 3 ln x over 2 plus c. This bit here is just a number. That's just a constant number. This bit here is also just a constant number. So what I can now write is 3 ln x over 2 plus c plus 3 ln 2 over 2. Now, what's actually just happened is, by me joining these two things together, it is 3 ln x over 2 plus a constant value. Well, so is this. This is 3 ln x over 2 plus a constant value. Okay. The only difference is, yes, we're calling them both c, it's just this is a constant value that is being added to 3 ln x over 2. This is also just a constant value that is being added to 3 over ln x plus 2. It just means that our c values in either of these equations are going to be different, but both of these are fine. Okay. In most cases, look, I'm going to happily accept this left one. It's a lot, that's fine if you want to do it that way. But you have to be able to do both methods if needed. All right, let's get into b. With b, there's no neat way of me stripping out a constant. It's because it's not just a number on the bottom with just a single x on the bottom, like this one was over here. Okay, so what that means is I write my 4, my ln, I put my 2x plus 1 back in my brackets, and I divide by the derivative of my bracket, and I put a plus c. Can I simplify the 4 and the 2? Yes, that'll give me 2 ln 2x plus 1 plus c. Done. So that would be the integral, or the antiderivative, with respect to x. Last one down the bottom here. This is a quotient rule looking question. Now, we need to be careful when it comes to antiderivatives. We don't have a neat little quotient rule in methods. what we can do is we can split this up into individual pieces and then simply anti-derive or integrate them separately. So what I'm going to do is I'm going to take this bit here and I'm going to crab claw or FOIL or distributive law that out. So let's get into it. 2x times 2x is going to give me 4x squared. 2x times 3 is going to give me 6x. 3 times 2x is going to give me 6x. And 3 times 3 is going to give me 9. So really what I've got here, if I join all these pieces together, this whole equation is saying to me I have 4x squared plus 12x plus 9 over x dx. So I'm integrating or anti-deriving that. Now that's still looking like sort of a quotient rule type question. However, what we can now do is before I even anti-derive these, I can strip each of these pieces apart into separate terms and divide each of these by x. So what that's going to mean is I'm actually going to be integrating 4x plus 12 plus 9 over x dx. And now I'm going to take this up here and do them piece by piece. So when we're integrating something like this, we just do each piece individually. So the integral with respect to x is increase my power by 1, divide by my new power. The next one, the integral of 12 is 12x, divide by my new power. Now this is where you fall into a false sense of security. You forget the 9 over x there needs to be a log. Okay, most of us want to go, yep, cool, 9x to the 0 over 0, zeros cancel out, cool, it goes away. No, 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 we can't do that. We have to remember that that's going to become 9 ln x over, divide by the derivative of the bracket, plus c. So we can now just tidy all this up. The 4 and the 2 is going to leave you with a 2. That 1, we don't need that 1. The divide by 1 on the bottom here as well, we don't need that, plus c. Lovely, all done. So the hardest part about this was expanding it out first and then being able to do what we did over here and break them all into these individual little separate terms.